Good afternoon, ladies and gentlemen. Welcome to the MetaMaterial webinars. Today, it's my great pleasure to introduce Professor Alexandra Boltasseva from the Purdue University. And she's going to show us how one can use the machine learning for photonics, for design, and to get actually new and very efficient properties in optics. Professor, it's your turn.
Thank you very much. Thank you. And thanks for inviting. As I just said, it is such a pleasure to be giving this talk on this webinar and to see familiar faces and names. I miss my colleagues so much, and I miss in-person events, and hopefully next time we can get together in a nice city of London, not for a Predator conference, but for a real one for sure. Again, thanks for inviting. I am very excited to share with my colleagues over the past year our recent achievements and our ideas of how we see the future of photonics and metasurfaces design and quantum photonics empowered by techniques that we adapt from machine learning and artificial intelligence. So I'll start just with a few words of introduction, why we care about optics. So for this audience, I don't have to convince anyone, but still. And then I move directly to our design and implementation of photonic devices and how machine learning can help us in this process. I will use a couple of examples in my presentation, and that's the research that's been ongoing at Purdue Group for some time. I will use how we advance and develop optimization processes for plasmonic matter surfaces with a specific application in mind, such as thermophotovoltaics and efficient energy conversion. I will also speak a little bit about materials and how materials as building blocks, as our essential technological platform will play into that and where they have a place into this machine learning vision. And I will also spend a little bit of time at the end of the seminar to talk about machine learning for quantum photonic measurements and largely for quantum photonics. Well, optical technologies literally change our lives. We are living in an interconnected society, and I don't have to convince you that we had tremendous advances that were brought to us by photonic and optical technology into areas of healthcare, renewable energy, digital economy, environment, agriculture, and as well as our social connections, as we are harnessing right now during the seminar. And the recent promise of quantum photonic technologies is leading us even further. We are witnessing the rise of quantum technologies that are exploiting and investigating different platforms for their realization. And photonics, of course, is taking very important part in that, because we are utilizing photons that are messengers with ultimately high speed. And what's also great for photonic quantum technologies is that photons are not easily interacting with matter, so they are exceptionally immune to decoherence. So building on these two pillars, we can foresee a lot of advances that photonic technologies can bring into quantum secure communication systems, photonic quantum simulations and computing, as well as quantum sensors that probably will enter the quantum technology and industry market first. At the same time with quantum, we are also in the middle of the second information and fourth industrial revolution, which is happening in the area of big data and artificial intelligence. Everything is big data now, and we are utilizing and needing more and more computational power, no matter what kind of research or kind of technology we're working on. So we foresee that merging the technologies of artificial intelligence or machine learning with photonics and the emerging QIST would actually be the enablers for the next generation of scientific discoveries and technological advancement. If we speak about revolutions in industrial or information revolutions, then it actually takes us back to building blocks, right? To very fundamental concepts that actually led to the first, second, and third industrial revolutions that the humanity have witnessed. And we are coming back to materials and materials at large, not only as building blocks and naturally occurring materials offered to us by nature, but also artificially engineered materials. And we have the father of the artificially designed optical materials with us today in the audience, Sir John Pendry, who proposed and is a pioneer of the area of metamaterials. And the area of metamaterials is where we realize that we have so far utilized components that have micrometer sizes or were built of naturally occurring materials for a very long time. And it is really appropriate right now to reconsider the whole concept of optics and photonics from the point of view of artificially created systems that allow us to build materials with electromagnetic properties that you can essentially design at will. Our ability to design these so-called metamaterials come from advances in nanofabrication. We are now able to make nano-sized building blocks that can be tailored and put together and produce artificial materials or artificial ultra-thin films with the properties that you need and that will bend and mold the flow of light at will. It also gives us a key to quantum nanophotonics, because ultimately it is the design of nanoscale components that will pave the way to on-chip quantum devices such as quantum sensors or quantum photonic circuitry for quantum communication systems. Specifically, one of the areas that actually emerged from a very broad field of metamaterials is the area of matter surfaces, which people see as really a paradigm shift in the whole area of conventional optics. These are essentially ultra thin, or let's say monolayer matter materials or matter surfaces that have tiny nano antennas that are designed in such a way that you can achieve the function which you have in mind with a single layer of optical nano antennas. So matter surfaces is seen as a technologically driven area, and it promises to replace not only bulky optics, but also to functionalities that are inaccessible or unavailable with conventional lenses or holograms. So you can design achromatic lenses or lenses that combine different properties in one. And there is a lot of investigations in the areas of time-varying matter surfaces as well. There is a lot of potential for designing dynamic and active systems that would be crucial for special light modulators, radar technologies, and many, many more. So potential impact of these artificially engineered materials range, as I already said, from flat optics replacing conventional ones to hybrid photonic electronic circuitry, sub-wavelengths on-chip devices such as photodetectors, improved data storage and recording, such as heat-assisted magnetic recording, single molecule sensors, many applications in biomedical areas such as drug delivery therapy, nano fabrication, energy conversion that I touch upon today, as well as emerging quantum information technology. Okay, let's start at photonics flow chart. So usually when you want to design a system, whether it's for exploration of fundamental effects or for just going and making a device, you start with the concept, right? And then you do numerical simulations. So the most natural or logical way for you to implement machine learning together with inverse design at this stage of the design, right? So that's what many people do. What is maybe less in use, but still people have explored, is how to use machine learning approaches in designing very efficient integration of the structures, such as in integrated circuitry. So I will show you a couple of slides with work of Helena Vukovic, where inverse design of very unorthodox looking and unintuitive designs provide very high efficiency. People have also explored machine learning approaches in testing of these devices, and testing of the devices can be compared to imaging techniques. Now, we know that people have achieved great advances in image recognition from sparse imaging for sparse data using machine learning techniques. What we also believe that there is very important missing component in this flowchart, and that's connecting the material platforms together with your design. Now, I already talked about metamaterials and Metasurfaces and how we can design these individual unit cells and nano antennas to direct and to tailor the interaction with light. However, the material building block that you are using for your nano antennas is another parameter for you to tailor, especially if this material dielectric permittivity can be tuned or tailored. So let's look at these processes and step by step. As I said, you start with photonic concept. It can be matter surface. It can be something in topological photonics, cavities, integrated waveguides, and then you do your design. Usually in the photonic design, you start with conventional numerical simulation. And in many cases, a simple shape variation is enough. Well, simple shape variation seems to be very simple, but we should not underestimate the power of this, because simple shape variation gave us a beautiful field of photonic crystals with their forbidden gaps, and as well as other areas of newer research, such as matter surfaces that exhibit bound state in the continuum. So beautiful physics does emerge from very simple shape variation. And let me give you just one example. It has not been applied or used machine learning, but just for as an example of simple shape variation in this all dielectric matter surface, you have high index dielectric cylinders in a dielectric host, and simply by changing the size of the cylinders, you can play around with resonances and achieve high Q resonances in the visible spectral range, polarization and sensitive response, which is also interesting and useful for application, but you will also create this near bound state in continuum points that you can utilize for many applications. So bound state in continuum is a very interesting regime. I will not go into details here. I will just mention that Usually, these are states that remain localized and have close to infinite lifetimes, even if they are residing inside the continuum. So one way to think about it is like a Fabry-Perot system. You have two resonances that are coupled to one radiation channel, and act as perfect reflectors near the resonant frequency. So you can sort of have a standing wave that is trapped in between, so you don't radiate out, and that's what we would call a Birck-like regime. So there has been a lot of research in photonic BIC systems, dating back to 2008, with first demonstrations in 2011. These structures can give you very, very sharp resonances with great localization in plane of this matter surface at one wavelength, and losing the localization at neighboring wavelengths with this very sharp resonance that can be interest for sensors and lasing application. But obviously, this is still simple shape variation, right? In most cases, you are not satisfied with a simple shape variation, so you have to go to more advanced optimization of the structures. So this part of my talk, as promised, I will use example of renewable energy conversion. And I will just put out this slide to remind you that if you look at the single junction photovoltaic cell, we do have an upper limit of about 33.7% for efficiency. What people have been investigating in the area of photovoltaics and energy conversion with nanophotonics is twofold. First, to design of course, structures that were able to provide your broadband absorption. But the second, and which is most important actually, is to find and develop materials that would be high temperature stable, because all this application would require very high operating temperatures. So at Purdue, we have spent many years looking and investigating materials that are ceramic, so that means that can withstand high temperatures, such as titanium nitride and zirconium nitride, that are very much like metals. So they also work like tiny nano antennas at the optical frequencies and can act as optical matter surfaces. So you see the design that we previously reported for extremely broadband light absorber. So solar irradiance on this graph is shown in black, and absorption of the matter surface is shown in red. So now, if you would like to utilize the energy that you absorbed from sun or from other energy source, what you have to do, you have to re-emit this energy in such a way that it coincides with the working band of the photovoltaic cell. So, for example, here there are some working bands of different semiconductor materials, and you see that in order to do that, in order to have efficient re-radiation of the emitter, you have to reach temperatures which are around 1500 C. So this is the concept behind solar thermophotovoltaics. You absorb as much as you can, and then you re-emit this radiation such that it coincides with the band of the photovoltaic cell. So this approach promises theoretically very high efficiencies, but you need very careful design and very stable temperatures, very stable materials at high temperature as well. So people have explored this with photonic crystals and other systems. So in our design, we are looking into high temperature stable matter surfaces. And we are utilizing a special class of matter surfaces that have been proven very interesting and promising for energy conversion applications. So there are many groups working on these so-called gap plasma matter surface absorbers. And in this case, we are dealing with the metallic mirror shown here in golden color. And then you have a dielectric spacer and an array of plasmonic nano antennas on top, and it is made of high temperature stable material, which in our case is titanium nitride. So this is the problem statement summary. We have a heat source that can be sun or just a gas burner or maybe a radioactive cell. And then you have to design a selective emitter such that it will emit and the emission will be efficiently absorbed by the photovoltaic cell. So now shaded area here is a working band of photovoltaic cell, gallium arsenide cell. You want to achieve the best performance, and for that your optimization problem is the following. You have to maximize this green part, which is power emitted in the region where your photovoltaic cell is working, and then you have to minimize the red part, which is emission out of the band and which gives you unnecessary heating. Okay, people have proposed several designs for achieving such thermal emitters. So you see this as like a square shape and cylinders, photonic crystal based. So what we started with is a very simple design of such a gap plasmon Metasurface. We have a titanium nitride mirror and a cylinder of titanium nitride on top. Now, if you run direct optimization like particle swarm optimization, you are not going to get much improvement. So you see you have some small variations in the efficiency of in-band emission, but that's it. Why is that? Well, you don't have a lot of degree of freedoms. You are limited by the cylinder shapes and the modes that can be excited. So what you can do after that, you should go into more advanced optimization techniques such as topology optimization, which has been applied in many areas of photonics already. So largely pioneered by people listed here: Eli Jablonowicz, Ole Zsigmond, Shanhui Fan, Jelena Vukovic, Stephen Johnson, and many others. It has become a very powerful technique to design unintuitive geometries for photonic crystals that are very efficient, waveguide components, metasurfaces, and topological photonics. So our approach is based on the same methodology and exactly the same technique as proposed by Ole Zsigmond for photonic crystals. So we'll again not go into details, but I will talk about the optimization problem itself. So we have a back mirror which is fixed. This is 300 nanometers of titanium nitride. We have 40 nanometers of a layer here of silicon nitride, which is your dielectric spacer to achieving this gap mode. And then we have a 120 nanometer thick optimization region. So what is optimization region? It's a region where you have some random distribution of air and titanium nitride. So in this random distribution of air and titanium nitride, you have to start with a random gas, and then you use this forward and adjoined FDTD simulations for the spectrum. You apply gradients, and then you do this in a iterative manner, and you also have to ensure that your design is stable, and it can also be fabricated. So this is what we are optimizing. Our target emitter spectrum looks like this. And this is what topology optimization can provide us. So topology optimization for titanium nitride thermal emitters will give you this funny looking structures that will give you efficiency that will go over. So the red line here is efficiency of a cylinder. So you can get up to 92% efficiency, which will be much higher than the cylinder. But this direct optimization is extremely time consuming, and we never know that you achieve the global maximum. You're starting with a random gas, and then you're probably achieving some local maximum. And it's very hard to introduce more parameters there. So that's a challenge in all optimization tasks in photonics. How you achieve the global maximum, it's how you address the time-consuming aspect of the process, and also you don't have intuition on how to pick the right initial condition. The solution for that is to leverage advances in machine learning techniques. So machine learning techniques have been already applied in photonics quite broadly. So deep neural network based or generative networks for design optimizations have been used for design of many components, including metasurfaces. So I will start with an example of generative adversarial network, or GAN, and its usage for our emitter design. Compared to direct optimization, where you start with random guess, and then most likely you will find a local maxima. What you're doing in GAN, so first of all, GAN has a generator and a discriminator. So if you have a training set, then your generator learns to produce patterns that are similar to training set from the random noise. And discriminator learns how to distinguish between the real and fake images and feeding it back to a generator. So these two are competing, and that's how the training is performed. So now imagine that we have trained our GAN system on designs that are already optimized. So these designs are optimized using direct optimization. So what you are feeding into your system are local maxima already achieved. So instead of starting from the random guess, in GAN, it actually looks at the patterns that correspond to highly efficient designs. And then you can hope that the system could find you the global maximum. So it also gives you a huge speed up. So we are, for example, generating 200 topology optimized designs in about 50 hours. Well, you then have to expand your training set because 200 design is not enough to train GAN. So you have to expand it to about maybe 8,000 or 10,000 designs. And then GAN produces 1,000 designs in less than 1 minute that are similar but different from the training set. You can run a few iterations of topology optimization on them and then look at the optimized designs as well. GAN has some limitations, so we have extended our work to variational autoencoder. So instead of just working with these shapes themselves, the direct data, what we can do using this technique is to use VAE to encode the topology optimized designs into so-called compressed or lattice-based. So what you are doing essentially is in this encoder is you are determining the main feature of the training pattern and compresses them into compact representation. And then decoder learns from this compact representation and reconstructs the real design. So why it's better? Well, because then you can work with this lattice-based or compressed representation instead of the design itself. And you can even expand it further. And this is the adversarial autoencoder is like a combination of GAN and VAE. And you can actually impose some restrictions on this latent space and make it very dense. And this gives you access to more generated designs. It gives you access to more unconventional outliers that you will not be able to access, for example, in GAN, and many other aspects as well. So let me show the results of this. So first, the computational time or efficiency. So comparison between direct topology optimization with adversarial autoencoder and adversarial autoencoder, where you actually use neural networks instead of direct optimization to refine the patterns. So you can actually have a drastic speed up in the computational power to do that. But what most importantly, in addition to speed up, machine learning gives you access to more efficient design. So we started with a cylindrical emitter here with the efficiency of 83% and compared even to direct topology optimization, machine learning can get you really close to ideal emitter. And these are examples of the corresponding high efficiency designs. So next step for us here, and yeah, I'm reporting very new results here as well, is to still search for that global solution. And this is a collaborative work between myself, Professor Vlad Shalaev, and Professor Sabri Kais. So what we are trying to do is to map this photonic problem into so-called quadratic unconstrained binary optimization, or QUBO model, that is routinely used for sampling for globally optimized solution. So now our idea here was, in fact, to explore whether we can use a D-wave machine for or quantum simulation for solving this highly constrained photonic optimization problem. So this is, as I said, a brand new ongoing work, and I could discuss it after the seminar, and I will not go into details. But what I would like to show you from our first results here is that when we are using the D-wave machine and utilizing this technique where we mapped our photonic problem into QUBO for the design of this thermal emitters, what we are getting here is really access to something, to some designs that do look like an outliers for our conventional training set. So this is our conventional optimized design, so shown here in blue. And what this D-wave technique will give you is located right here, shown in orange. And that's exactly what we want. We want our system to be able to give us designs that would be outside of the training set and lead us to the globally optimized solution. So now my next point in this talk about machine learning will be introducing or talking just a little bit about optical materials themselves. Well, first of all, everything is about building blocks. You cannot really design or implement any material, whether it's for fundamental studies or for technologies, without materials. We should never underestimate the power of constituent materials. Well, first of all, constituent material themselves can provide you a knob for tuning the parameters of your metamaterial or metasurface. People have been investigating tailorable, adjustable, and dynamically tunable material now for many years, and we have achieved a great success in tailoring the dielectric permittivity of constituent material. But yet another thing is also important, such as new materials and the new properties will lead to new effects. So we are opening new chapters of nonlinear optics now with materials with refractive index near 0, and this has been enabled by the progress in photonic materials with a dielectric permittivity which is close to 0. And I already talked about the importance of materials that are refractory or high temperature stable. So all these aspects of material platforms do play a critical role in our ability to design and implement efficient photonic structures. And by now, the community of photonics researchers have been demonstrating amazing progress in essentially providing materials with dielectric permittivities that you want, right? Ranging from positive dielectric permittivity for dielectrics to metals, and even materials in this interesting epsilon near zero region, such as transparent conducting oxides. So the ability to tailor the optical response becomes important for structures like metasurfaces and metamaterials, where you already have a lot of ways to engineer the optical response. You also want to be able to adjust the dielectric permittivity of the constituting material itself. In contrast to conventional metals, ceramic materials such as titanium nitride and zirconium nitride do have this possibility. You can make them less and more metallic, as shown on this graph. And epsilon near zero materials that can be utilized, realized using transparent conducting oxides are also extremely tailorable and adjustable. So this is an example of aluminum and gallium doped zinc oxide. They have a zero crossing for their real part of dielectric permittivity in the near IR range. So they can work both as a semiconductor, so dielectric materials, and metallic materials in different ranges in the telecom, and enable a range of interesting applications around the ENZ point. So largely pioneered by Nadine Getter and J.L. Liu and others, people have been investigating a lot of exotic physical phenomena based or concentrated around this region. Another very interesting direction in the area of materials that I would like to just mention today is the area that what we call a transdimensional material. So this is somewhat between the 2D and the 3D. So it's not a monolayer system as graphene, even though 2D as a research and a great area in itself, but rather it's a several monolayers of material that can also provide you the ability to tailor the properties and achieve extraordinary tunability, switching, and nonlinear responses. So, for example, ultra-thin metal films that are known not to be tunable in their bulk form become electrically tunable in this ultra-thin regime, as predicted by Javier Garcia de Baja. They actually promote unique light-matter interactions in this highly confined light regime, as predicted by Marin Seljacic, including effects such as enhancement of indirect and forbidden transitions, and you can also adjust the optical properties by strain and stress as in semiconductors. So the next step for us, and I believe for photonic device community as well, is to merge our knowledge, our understanding of optical materials and optical material platforms with our knowledge of inverse design, and now coupled with machine learning, to actually move towards such a hierarchical machine learning where the system will actually not only tell you what the best shape or of your structure should be, but also suggests what the constituent material should be, what would be the best architecture to achieve the function in mind. Moving on along the photonic flow chart, as I said, at the point of testing the device, we have seen great advances in image reconstruction using sparse data, but people have not applied machine learning to a large extent in other areas of optical measurements. And one of the biggest challenges in quantum photonics is connected to the complexity and resource-heavy quantum measurements. So this brings me to the next topic of enabling integrated quantum nanophotonic circuitry with hybrid platforms. You can imagine that in such a future platform, you would probably like to have maybe an emitter of a single photon that would be very effectively coupled to a nanophotonic waveguide. In order to achieve the efficient functionality, you should be able to design such a hybrid platform with optimally designed systems and interfaces, like coupling from one system to another, and essentially leverage the advantages of photonics, electronics, plasmonics all together to achieve the high performance. Just to give you one example, this is a recent work. This is a collaboration with Vlad Shalaev and Simon Bogdanov. So we're investigating the quantum emitters and specifically nitrogen vacancy centers in nanodiamonds in a plasmonic cavity. So what happens here is this nano antenna plays a dual role. It provides the enhancement of the field in the gap, and this high self factor leads to a faster emission of your radiation. And the second function of this antenna is to outcouple into free space. So you really have, you enable a really bright quantum emitter in this way. So we registered intensity enhancement of about 90 times with about 10 of millions photon per second. The problem with this whole field, or I would say not a problem, but a challenge, is that every time you're dealing with a quantum system, and in photonic quantum, it means a single or a pair of photons, you are dealing with extremely low intensities, and you are dealing with very long characterization time that you have to spend on each emitter. In our case, we have substrate, for example, with an array of nanodiamonds. It can be thousands of them, and you have to spend from 1 to like 20 minutes of collection time using quite involved measurement techniques, and this is called measuring of the second order autocorrelation function. For measuring the so-called G2. So G2 is the second order autocorrelation function that actually gives you indication whether you have a single photon emitter or non-single photon emitter. And this takes time. So if you think about the future quantum photonic circuitry, and you will need both rapid characterization and classification of emitters into good and bad, you will have to do it in a different way. So, and what we have been implementing here is we are using approaches in machine learning and for recognition from the sparse data. So what we are doing here, instead of waiting and collecting the data on each emitter for a long time, we train our classifier on sparse data. And the sparse data is taking only 1 second measurements on each emitter. So the training of this classifier is based on collected sparse data and retrieved corresponding labels. So we know the corresponding labels beforehand, whether it's a good or single photon emitter or a bad emitter. And then we can actually use this classifier to tell us with a high fidelity whether we are dealing with single photon emission or not. Potentially, this is a very powerful approach because it can also lead to rapid quantum super resolution imaging. So again, essentially what you can do is you can imagine that you are scanning your surface, and this can be just any quantum emitters. Maybe it is a two-dimensional materials with quantum defects, but you can scan and you can measure this autocorrelation function G2 at each point. And again, with high fidelity, it will tell you whether there is a single photon emitter there or not. And you can actually achieve both super resolution imaging and speed up of characterization this way. So this is what we see as one of the very important and critical steps in the area of quantum photonics. And another one, which is related to conventional photonics, but becomes more crucial in the area of hybrid quantum photonic circuitry, is integration, as I already mentioned. So people have already achieved a great success in integrating or in designing this unconventional looking systems for efficient couplers and waveguides. And what we are looking into right now is how to apply both topology optimization and machine learning assisted optimization for efficient design that would provide us with efficient hybrid photonic system. Again, for example, consisting of a quantum emitter, a plasmonic antenna, and a waveguide. So in this photonic or quantum photonic integration, we can use similar approaches that I've showed for the area of matter surfaces for energy conversion. And these are just examples of some topology optimized designs and that can be implemented for quantum photonic devices. So overall, where we see the advantages and critical advancements that machine learning can provide in the area of quantum nanophotonics would be quantum measurements, as I said, applying classifiers that can very quickly tell you whether you are dealing with good or bad emitters, quantum device optimization, as well as future rapid prototyping and deterministic assembly. Because ultimately you would want to create these on-chip devices by rapidly selecting and maybe placing quantum emitters on a chip, but all this would require tremendous speed up and enhancement of resolution of your quantum techniques. With that, I would like to sum up and bring this photonic flowchart one more time. We do believe that machine learning is indeed will become a critical component at each stage of photonic process, and ultimately even lead us to new discoveries and new physics that machines will show us. With that, I would like to thank our big photonics team at Purdue. So my major collaborator and dear husband, Vlad Shalayev, Professor Alex Kildashev, the entire group, and specifically our stellar postdoc Shaksala Kidashev, who is in fact on the market looking for academic position. He is, I don't know how we will live without him, because he entirely propelled the area of machine learning in this group. And with that, I thank you for your attention.
Thank you very much for this very nice talk. So now we have time for questions. So please just ask your question, or you can write it in the chat. So just feel free to come.